Hello dear students, welcome you all. In this lecture, I am going to discuss about the helicity of elementary particles, right? We have seen in the earlier lecture that parity was violated in weak interactions. That's why we have solved the tau theta puzzle. That was big riddle puzzle in high energy physics, and T.D. Lee and C.N. Yang were the two physicists who have suggested that the uh, parity is violated in weak interactions. That's why we are getting different parity in the decay modes of tau and theta particles, right? So T.D. Lee and C.N. Yang suggested that the violation of the parity conservation in beta decay is because of the longitudinal polarization of the emitted electron neutrinos, right? Now in order to measure this polarization, they suggested a term, right? That term is known as helicity. The state and degree of longitudinal polarization of the particles that are electron and neutrinos which are emitted in the beta decays, that degree is measured by a term that is known as helicity, and it is written as h is equal to s dot p divided by vector. Both these are vectors, vector magnitude dot p vector magnitude, right? So here s is the vector in the spin direction, p is the vector in the linear momentum direction, right? So if I expand it, then it will become s into p magnitude, right, cos of theta divided by s into p, right, magnitude. So I got what I got. I got helicity is equal to cos of theta. So what is the theta? Theta here is the angle between the direction of the spin and linear momentum of the particle that are emitted in that decay, right? Here we are taking the case of beta decay because T.D. Lee and C.N. Yang has first measured and suggested that the parity conservation is violated in the beta decay, right? So we are taking here the case of beta decay. So here, as I told you, that this helicity will depend upon the value of theta. If theta, is in such a way that the spin direction and linear momentum direction of the particles are parallel to each other, then the angle between them is zero. Theta is positive +1, right? This is the situation. If theta is 0, helicity is +1, right? But if they are anti-parallel, this is the case, you can say here it is the spin direction and it is the linear momentum direction. Here it is the spin direction and it is the linear momentum direction. You can see here both the spin and linear momentum are in the same direction, right, of the particle. But in this case, the things are opposite, right? So the first case is the case of positive helicity +1, and this is the case of negative helicity -1, because when the angle between the S and P is 180 degree, you can put here 180 degree, the helicity will become negative, right? So this is the way of measuring the helicity of any elementary particle. Helicity basically tell us about the relation between the orientation of the spin direction of that particle and linear momentum direction of that particle. We can say we can compare this with the screws. We can say that if a screw is a right-handed screw, then in that case helicity will be positive, and if that screw is left-handed screw, helicity will be negative. Now what is right-handed screw and left-handed screw? We know very well what is screw rule. In right-handed screw, when the screw is rotated counterclockwise, then it moves upward, it proceed upward, right? uh, or we can say it closes, right? I have this pen, but this is not, I can show you this example again. This is not having screw. This is the pen, right? Now you can see here, right? This is the pen that I'm talking about. Let me tell you this you can see now. Now this is the pencil that I have. This is the screw, you can say. Now I am putting it here. Now I am rotating is in this way, counterclockwise, right? When I am rotating it counterclockwise, this pen is getting closed. This screw is getting closed. It means it is moving forward, right? So we can say this is a right-handed screw, right? But in some screws, the rule is opposite, right? When we are rotating them counterclockwise, they come out, right? So it means their spin direction and linear momentum directions are opposite, right? So that's why they are known as left-handed screws. But in right-handed screws, when they are rotated counterclockwise, they move in the same direction as their spin direction is there, right? So here in this case of helicity, we can say that if a particle is behaving like a right-handed screw, then in that case we can say the helicity is positive. But if it is behaving like a left-handed screw, then its helicity is negative, right? So now, why this helicity term is important? T.D. Lee and C.N. Yang suggested that we know parity is a good quantum number in high energy physics, right? And the system has either positive parity or a negative parity, right? And if a system is going to conserve the parity, then the helicity must be equal to 0. We will see in the coming lectures. In that case, the helicity of the system must be equal to 0. But if the helicity of the system is observed different from 0, it means that reaction, that system is going to violate the parity conservation, right? We know very well that parity can be positive, can be negative, can be 0. But helicity, if helicity is other than 0, then that particular system, that particle in that interaction is going to violate the parity conservation, right? So this is about the helicity. Now I'm going to tell you how we can measure the helicity of electron neutrino. It is very important because we are studying the helicity in beta decays, and we know very well in beta decay reaction what we got. We got a reaction in which either neutron convert into proton plus electron plus antineutrino associated, or either proton convert into neutron plus positron plus neutrino, or proton plus electron, right? That give you neutron plus sorry, here it is equal to neutron plus neutrino associated with the neutrino. So these are the three different reactions in beta decay that can take place, and we can see here that in all these reactions we are getting a neutrino particle. In first one we are getting antineutrino associated with the electron. Now we have to measure the helicity of electron neutrino here in these reactions, but we know very well that it is extremely difficult to observe the neutrino in the nature because its interaction with the matter is extremely low. We can't observe it, we can't detect it, right? That's why it remain out of the observations detections for a long time, because it is totally invisible particle. It does not interact with matter, it don't have any charge, right? So that's why it is very difficult to detect the neutrino and measure its properties. So here now we are going to see how we can measure the helicity of electron neutrino, right? So to measure the helicity of electron neutrino, the method that was suggested by Goldhaber and his co-workers in 1958. Goldhaber and his co-workers in 1958, right? They suggested a way to measure the helicity of neutrinos, because we know very well that as told by T.D. Lee and C.N. Yang in 1956 that the parity conservation is violated in weak interactions, particularly in beta decay. So we know very well beta decay involved the interaction between the electron and neutrino. These types of reactions are involved, and we have defined here that the helicity is going to tell us whether the parity will be violated or not, because we are going to measure the helicity, right? So here we have to now invent a technique to measure the helicity of a neutrino, because only then we can tell whether the parity will be violated or not. But the thing is, To measure the helicity of neutrino, it is extremely difficult. What Goldhaber and his co-worker suggested a method that I am going to discuss with you. Sorry. So, but they suggested that let's suppose a parent nucleus that is in the ground state and having spin I is equal to 0, right? It absorbs the innermost. They consider a electron capture process, right? This process, right? It absorbs the innermost electron, that is K shell electron, and it convert into a daughter nucleus that is in the excited state, and that has a spin is equal to 1, or I is equal to 1, we can say, and plus electron neutrino. This is the reaction that is going to happen in this electron capture process, right? They took this type of reaction, right? That was imagination at that time. They thought that let's consider reaction of the electron capture process which took place in this way, right? But we require a parent nucleus that has spin 0 and it is in the ground state. It absorbs the innermost K shell electron, that it convert into a daughter nucleus. That nucleus is in the excited state. That's why I have marked star here. It has spin 1 and electron neutrino is emitted, right? Now let's apply law of conservation of linear momentum. Linear momentum P. Now if we look at this reaction, right, we can see, as I told you, that this entire process where the parent nucleus captures a K shell electron, it took place in nucleus that was at rest and that was in the ground state. It means the linear momentum, initial linear momentum should be equal to 0. We can say P initial is equal to 0. Now if the law of conservation of linear momentum is obeyed, then the P final means the linear momentum of the final state, that must be equal to 0, right? The linear momentum of these two particles, sum of the linear momentum of these two particles must be equal to 0. It means what I got from here? I got here from here, this was the parent nucleus, right? Positively charged, that is represented as a plus. I am representing here as the electron separately, but this electron is not separate. In fact, it is the innermost electron of this parent nucleus. Then it convert into a daughter nucleus, right? That is by star plus this is a particle that is emitted. Now, as per the law of conservation of linear momentum, the linear momentum of this system, this plus this, must be equal to 0. It means these two particles are moving in a opposite direction. Only then the linear momentum can be equal to 0. So what I got from here, that the linear momentum of P, linear momentum of by star must be equal to minus linear momentum of electron neutrino. These two linear momentums are in opposite direction. So that's why we will get the total linear momentum is equal to 0, right? Now, as this nucleus is in excited state, right? So it must come down to the ground state and its spin must become equal to 0, because only then this spin will be conserved. Otherwise, here's 0, the electron spin is either plus or minus 1 by 2. Here electron neutrino spin is either plus or minus 1 by 2. So this nucleus must come to the ground state and it must have a 0 spin, right? So in the next step, when this nucleus, excited nucleus, it comes to the ground state, then it go like this. It emit by plus gamma ray photon, right? Now it is in the ground state with I is equal to 0, right? So now when it comes to ground state, its spin become equal to 0 and a gamma ray photon is emitted, right? Now, as I told you, that this nucleus was in the excited state initially by this was, and it was moving in this way, right? Now if I apply the law of conservation of linear momentum here in this reaction, right, then what I should get? As this nucleus is moving, you can see here it is moving in this direction, right? I can say excited nucleus. Now it comes to ground state and it comes to the rest, right? It is at rest, right? So what should be the direction of the motion of gamma ray photon? In this way. Only then the linear momentum will be conserved, because both of them are moving in the same direction, right? So it means the gamma ray photon will move in the same direction and the excited nucleus was moving. So I can represent gamma ray photon here. It is emitted in the same direction as the excited nucleus was moving. So from here, when I applied this law of conservation of linear momentum here, what I got? I got that the linear momentum of the gamma ray photon must be equal and opposite to the linear momentum of electron neutrino, right? This is the thing that I got from here, right? It is very, very important. We have to take note of it, right? What we got from here, that the linear momentum or the direction of the motion of gamma ray photon is always, sorry, I forgot to place a negative sign. It is always opposite to the direction of the motion of electron neutrino, right? Now let's see what happened to the law of conservation of angular momentum, right? So let's see what happened to the conservation of angular momentum now in this reaction, entire reaction. Conservation of angular momentum. So this entire reaction is represented as a x plus electron that gives you by plus gamma ray photon plus electron neutrino, right? Now here I have this I is equal to 0, right? And I is equal to 0. Both these are in the ground state. This is parent nucleus, this is daughter nucleus, this is electron. Now if we apply the law of conservation of angular momentum, now this nucleus has spin 0, angular momentum 0, this has also 0. Two possibilities for electron, plus minus 1 by 2. Two possibilities for electron neutrino, plus minus 1 by 2. And two possibilities for gamma ray photon, plus minus 1. Let's come to the first possibility. When I have this as 0 plus 1 by 2, that will give, if the law of conservation of angular momentum hold good, in that case, if 0 plus 1 by 2 is there, then there should be 0 plus 1 minus 1 by 2, because only then I will get 1 by 2 is equal to 1 by 2. This is the first case. In second case, 0 minus 1 by 2, then I should get 0 minus 1 plus 1 by 2. Only then I will get 1 by 2 minus is equal to minus 1 by 2. So these are the two conditions, right, under which the law of conservation of angular momentum will hold good. So now you can see here that in both these conditions, if look at this spin of gamma ray photon and the electron neutrino, plus minus, here minus plus, it means in both the cases the spin of electron neutrino and photon, they are opposite to each other, although they have different magnitude, but their direction is opposite in both the cases, both possibilities. So I have represented these both possibilities here. This is for photon and this is for a neutrino. So you can see here the spin direction of the photon is always opposite to the spin direction of electron neutrino. We got from here, right? And we have also seen that the linear momentum direction, here I have written, it is always opposite to the this. So I have also drawn here. So I got the linear momentum is also always in opposite direction to the neutrino. So this is the first case. Now what does it means? It means if I want to measure the helicity of neutrino, because helicity is going to tell us about the angle between these two, spin and linear momentum of a particle. So it means we don't need to measure the helicity of neutrino. Even by measuring the helicity of photon, I can measure the helicity of neutrino, because they will have the same helicity, because you can see here they are in the parallel direction, they are also in the parallel, right? If second case can be there, let the spin is in this direction and the spin of the neutrino will be in this direction, then in that case, because they are both opposite, if the linear momentum is in this direction, it is in opposite direction. This is the second situation. So in this case, both these vectors S and P, they are in opposite directions. 180-degree angle is there, so helicity is a negative, right? And here helicity is a positive. So you can see here from this discussion, it is very clear that if we want to measure the helicity of neutrino, then what we have to do? We have to simply measure the helicity of a photon, gamma ray photon that is emitted in this reaction, right? We don't need to go for a neutrino. The neutrino will have same helicity as the photon will have, right? So how this problem of the measuring of the helicity of neutrino was solved by Goldhaber and his co-workers in 1958. But what was the requirement? This is a theoretical prediction. Now what we need? We need a suitable nuclei that fulfill all these conditions, right? That must have spin 0 in the ground state. It must undergo an electron capture process, and the electron capture must be from the innermost K cell. Then it go to the excited state, then and emit an electron neutrino. Then it come down to the ground state with the emission of a gamma ray photon. So all these conditions should be satisfied, right? But if these conditions are satisfied, then we can measure the helicity of a neutrino by simply measuring the helicity of a gamma ray photon. So this is the way how we can measure the helicity of a electron neutrino. This is the way. Now in the next lecture, I will discuss how the helicity was experimentally measured by picking up a suitable nuclei that was predicted by the Goldhaber and his co-workers, right? So this is all about the helicity. Once again, I'm telling you that helicity is going to tell us about the violation of parity conservation in any reaction. Because if helicity other than 0 is observed in any nuclear reaction, that reaction is going to violate the parity conservation, right? So thank you very much.